get rid of me, so it will be probably coming on the regular basis. Okay, so as you see, the title is indicated. So first of all, it's a joint work with Yarek Kedra from Aberdeen. And the idea of this talk is the following, is to show that certain very natural norm on subgroups of groups of homeomorphisms can be stably unbounded. And another idea of this talk is actually to show you that when it's restricted to the group of Hamiltonian diffeomorphisms, then not always Floer-theoretic methods are needed to say something about this norm. And today's talk will be mostly topological and geometric group theory, and some corollaries actually will apply to the group of Hamiltonian diffeomorphisms of a symplectic manifold. Okay, so let me start with a setup. One M is a complete Riemannian manifold. Let's say dimension greater than equal than 2. 2 mu is a good measure. That's not my my name. Measure on M. So this is a Fati terminology. So maybe I should write it like this. By meaning, you can think about Lebesgue measure. Basically, what it means is that basically it's a non-atomic measure which is positive of all non-empty, open non-empty sets. Okay, so this is what it means. So I'm not sure this is a good name for it, but I just stick with this name. Okay, and 3 homeo 0 mu. This is the identity component of measure-preserving homeomorphisms of M. Okay, so you can ask me, of course, what's the topology of it, but any topology you put will be fine for us. But usually, since so on this group, usually I would put maybe C0 topology. This would be the better one. And if I will think about subgroups of this group, I will put C infinity topology if this group of diffeomorphisms or symplectic homeomorphism or Hamiltonian diffeomorphisms. Okay, so you should think about two diffeomorphisms close if all the derivatives are close, and if it's in homeo, they just close in C0 topology. Okay, so that's probably the better topology to use. So this is the identity component of the group of measure, say mu preserving homeomorphisms. So if M is open, by the way, I'm going to talk only about compactly supported. So this is by the definition, all my homeomorphisms are compactly supported. Okay, I will not write the letter C, just not for not abusing the notation. And 4 is usual notation. Ham M is a group of Hamiltonian diffeomorphisms, which is a subgroup of diff 0 M mu. So this is the group of volume-preserving diffeomorphisms of M, more precisely the identity component, which is a subgroup of homeo 0 mu. So what I'm going to talk about today, I'm going to focus on these subgroups, or usually their commutator subgroups as well. Okay. Say it again.
Mu is the real field measure when M is symplectic.
So thanks. I'm cheating a little bit during my talk, and I will be cheat a little bit during my talk all the time. What I mean is, in this case, you just can take here any symplectic form. It doesn't really matter. Okay. So of course you can take the one which is compatible as well. This is your question. but all the results will apply to anyone, okay? So this is, I will be cheating a little bit during my talk on this, okay? But thank you. So now I will give a definition of a fragmentation property that most of you know. Yes?
I understand cheating, but maybe it's too much. Because Hamiltonian will not be a subgroup of the different one.
Say it again. So Hamiltonian will be the subgroup of symplectic, of simp0, right?
Yeah. But it does not preserve the measure mu unless the measure mu is the real measure.
You're right completely. So what I'm saying is the following. So you can take here the, let's say, the symplectic form, right? So symplectic form in the power m, it's div0, right? So then you can extend it to the measure by the Kolmogorov results. You can extend every measure, basically, it is this type. You can extend it sorry, my manifold actually, it's a smooth manifold. So this is a measure of my manifold, right? Mu. And then I'm looking all my homeomorphisms which preserve this measure. So this is not a topological manifold. Am I okay with this? So again, I'm looking at the group of Hamiltonian diffeomorphisms.
You want to see it as a subgroup
Yeah.
of measure preserving
Homeomorphisms, yeah.
homomorphisms or diffeomorphisms.
Yes.
But measure preserving with respect to the measure mu.
Yes.
And the Hamiltonians will not be a subgroup of those unless mu is related to the symplectic form.
Yes, you're completely right. But I can take mu related to the symplectic form. This is what I'm saying. But then the results are independent of this mu. This is what I'm trying to say, okay? So this is my cheating a little bit. Just think about this. Think about this group. Then think about omega n, which is exactly div0 m mu. And think about this mu. So this is enough for the talk. But it applies to any mu, okay? It applies to any mu which is a good measure. This is what I mean. It's not a subgroup, it's true. It's not a subgroup. So what I'm trying to say is the following. So then forget about that it's a subgroup, okay? This is what I'm trying to say, okay? Forget about this, then there will be certain definition on this, and then certain results will apply. But again, if you want, just think about it, take a standard symplectic form, any symplectic form, take omega in the power n, and take this mu. Okay, so this is what you should think about during this talk. All right, so, and then maybe 5. So this would be A. Let G be a subgroup of homeo 0 mu such that first G is not a subgroup of div0 mu and let beta be the following collection of balls B in M such that the measure of B is less than equal than 1 and B is a topological ball. So more precisely, if you want, this is an embedding of topological ball inside of M. So just take a standard ball, and this is the topological embedding of standard ball inside of M. So if M is of dimension n, so this is the topological embedding of Bn. Okay, so this is a collection of all such balls of measure less than equal than 1. So we say that G admits fragmentation property with respect to beta if every diffeomorphism F and G for every, there exists, let's say, diffeomorphisms H1 up to Hm in G, such that support of each hi belongs to beta, or not belongs to beta, it's inside of some, let's say, bhi, which belongs to beta, and f can be written as a product of h1 up to hm. Okay? So this is a standard fragmentation property with respect to those balls. And then 5b, so this is a technical condition, just is basically everything is the same. So in this case, G is a subgroup of diff 0 m mu. And in this case, I will take beta prime. So this ball is not topological, but this ball is smooth. That's all. And again, I will take the fragmentation property with respect to smooth balls. I will just be needed this the end. So again, everything is the same. Thing is the same with respect to the collection beta prime, which is, again, B in M, so that mu of B less than equal than 1, and B is a smooth ball. Okay. So then we say in this case that G admits a fragmentation property. It can be written as a product of homeomorphisms or diffeomorphisms, so that each one is supported in a either topological or smooth ball of a measure which is less than equal than 1. Okay. So what I would like to study is the following. So is going to study the following object, G, with respect to the fragmentation norm. I'll tell you what it is, of course. So when my subgroup G, or when my group G admits a fragmentation property, then there is a natural conjugation invariant norm, which is called the fragmentation norm. So this is a just word norm with respect to the generating set of diffeomorphisms, which are supported in balls of measure less than equal than 1. In other words, fragmentation norm of diffeomorphism G, or of a homeomorphism F, it's a minimal number M, so that this F can be written as a product of H1 up to HM, so that each one is supported in a either topological or a smooth ball. Okay? And automatically, this is a conjugation invariant norm. It was studied quite extensively in the case of the group of Hamiltonian diffeomorphisms, and also in some other cases. So what I want to try to show today that in many cases, this norm will be stably unbounded, and then the hardcore symplectic methods are not needed in order to establish this result. Okay? So before that, I would like to give a definition of conjugation invariant norms and its importance. Any questions so far? No. Okay. So now I will have to give you several definitions. One, it will be definition of conjugation invariant norm of quasimorphisms. Those are objects that come from geometric group theory, and relative quasimorphisms. Some of you are aware of it, some of you not, but I will just still give the definitions. So first definition, conjugation invariant norm on a group G is a function, let's say, nu from G to 0 infinity, such that 1 nu of G equals to 0 if and only if G is identity, to nu of G equals to nu of G minus 1, 3, there is a triangle inequality. So this is what is called norm on the group is less than or equal than nu on G plus nu on H. And 4, there is a conjugation invariant. So nu on H, GH minus 1 equals to nu on G. Just to emphasize, if you have such a norm, then you always have a bi-invariant metric on your group. And we would like to study certain bi-invariant metrics. How would you define it? You just define the distance between G and H as this norm of G multiplied by H minus 1. I will not write this down, but this is quite obvious. Then this metric will be invariant from the right and from the left. So it's obvious that such norm always exists, right? Just give 1 to any number, to any diffeomorphism, or just to any element of G, and take 0 to the identity. But this is not really interesting. So what is interesting is the question is whether, given a group, whether there exists such a norm which is unbounded. So then I will give you a definition of unboundedness, and more interesting, whether it's stably unbounded. Okay? So this is maybe 1. And I would say this is A, B, C, and D. 2, G is called bounded if every conjugation invariant norm on G is bounded. So if you're completely bored, you can try to prove that SLN Z, when n is greater than 2, is a bounded group. This is probably, in first sense, really non-trivial result. On the other hand, it's not so difficult to prove. Okay? And on the other hand, SL2Z, it's unbounded. And this is kind of not so strange because there is a F2 inside of finite index. So, and I would say, maybe I would say it, don't write it. Otherwise, if there exists at least one which is unbounded, then the group is called unbounded. Okay? So 3 maybe. Otherwise, G is unbounded. And 4, G is called stably unbounded if there exists a conjugation invariant norm nu and G in G such that the limit, let's say n goes to infinity, of nu G in the power n divided by n equals to C. I will not write it equal, it's just greater than 0. Okay? So just by the definition of a norm, by the way, because this is a subadditive function, then this limit exists. Okay? And then since this limit exists, it could happen that your norm is unbounded, however it is bounded on every cyclic subgroup, for example. And then this is automatically 0. Okay? So those are two different notions. Of course, if it is stably unbounded, then it is unbounded. Okay? So then I just maybe should emphasize importance about all those and several open questions still in the field before I continue. So I think this terminology is due to Burago, Ivanov, and Polterovich about, I think, 12 years ago, something like this. And still there are some quite important, I think, and quite difficult questions which are open. So maybe let me write them down, at least a few of them. So some questions, open questions. Think about diff 0 S3 vol. So this is a standard three sphere. Nobody knows whether this group is bounded or unbounded. So bounded or unbounded. This is an open question. Maybe in case of groups of diffeomorphisms, several people proved the following result. If you think about only div 0 of M without any condition of measure preservation or volume preservation, then in most cases those groups are bounded. What do I mean in most cases? So take all the dimensions except of 2 and 4. It is known. This is due to either Burago, Ivanov, Polterovich, or to Tsuboy. In the dimension 2, it is known for spheres and for disks. It is not known already if you take the genus greater than or equal than 1. So this is another open question. Just take diff 0 of sigma g, g greater than or equal than 1. In several cases of 4-dimensional manifolds, it's also not known. Okay, and that's it. So this is the only cases bounded, again, bounded or unbounded. There's a very natural norm. So in particular, for groups of diffeomorphisms, many groups are perfect groups, which means that they're equal to the commutator subgroup. And then there is a very natural conjugation invariant norm, which is just a commutator lengths. Right? So what's the commutator lengths? Again, there is just a word metric with respect to the commutators. And then, for example, it is already not known if you take, let's say, Ham of R2 minus 2 points, x and y. It is not known whether commutator length is stably unbounded or not. Okay? So is commutator lengths stably unbounded. So more precisely here, you probably should take the kernel of Calabi homomorphism, because this group is not simple, but then the kernel of Calabi, it is simple. Okay? And on this group, you have a commutator lengths, and then, but I will still state it in this way because I will talk about quasimorphisms, and this is in some sense generalization of this stable commutator lengths property, stably bounded or not. And there's many other open questions. Okay, so now I would like to give a definition of a quasimorphism and of a relative quasimorphism with respect to a given conjugation invariant norm, and then I will state the results and then try to indicate maybe the proof of the result or something like this, depending on the time. Okay? All right. So there's another definition. The function, say, psi from G to the reals is called quasimorphism, sometimes quasi-homomorphism. If it is almost homomorphism, which means that if there exists some C greater than equal such that for all G and H in G, we have that psi of GH minus psi of G minus psi of H is less than equal than C. Okay? So natural examples are homomorphisms or bounded functions, right? But think about your group when your group is simple, for example, which is many cases of groups of diffeomorphisms, then there are no homomorphisms to the reals, and you would like to get rid of bounded functions. So then this is definition maybe 1. So given a quasimorphism, you can always homogenize it, and these are objects that we're going to work with. So phi bar applied to G, this is just a definition. It's a limit when P goes to infinity, phi G in the power of P divided by P. So again, if you're bored, you can check that this limit exists. So first statement that the limit exists. Second statement that this limit is a quasimorphism, but other statements are more important. So let me write maybe the facts. That phi bar of GH equals to phi bar of G plus phi bar of H if GH equals to HG. So whenever restricted to abelian subgroups, this is just a homomorphism. This is A and B. Sometimes they're called quasi-characters because they're constant on conjugacy classes. psi bar of h, g, h minus 1 equals to psi bar of g. And in recent years, several constructions of groups of quasimorphisms appeared on groups of Hamiltonian diffeomorphisms, volume-preserving diffeomorphisms, not really homeomorphisms. So this is a certain extension I'm going to talk about. But the problem is the following. So all the constructions that appeared either in the topological setting or when the construction uses certain spectral invariants in the case of group of Hamiltonian diffeomorphisms, in all those cases, we can construct quasimorphisms only when our manifold has a finite measure. So there is not even one known construction, at least to my knowledge, of a quasimorphism that uses when your manifold has infinite measure. So maybe the simplest example would be just think about R2 minus X and Y. I'm talking about compactly supported. It is not known whether there exists a quasimorphism on this group or not. And take your favorite symplectic, or just take your favorite manifold, take your favorite group, diff0 volume preserving or Hamiltonian diffeomorphisms, try to construct, and since the quasimorphisms are in duality with stable commutator lengths, it's quite an interesting question. Although for those such of groups, many people constructed, and I'm going to give today another construction, not of a quasimorphism, but something which is called relative quasimorphism with respect to certain conjugation invariant norm. And this would be my next definition, and then finally I can state the result. Okay.
You get the example R2 minus 2 points. Where did you take the 2 points? Why not just take 1 or take 6?
Excellent, excellent. So no, that's a very natural and good question. So I wanted to avoid it, but then I have to answer it now. If you take first 0 points, Ham of R2, there are no quasimorphisms. Okay, there is a Calabi homomorphism, but even on the kernel there are no quasimorphisms. This is not a difficult. There is something which is called in geometric group theory Kottchek trick. I can talk about it later, but not during this. And then, although this group actually admits a conjugation invariant norm which is stably unbounded, there was a big question for some, I don't know, big or not, but there was a question several years ago which asked whether quasimorphisms are in duality with conjugation invariant norms. Because whenever you have a quasimorphism, you can construct an unbounded conjugation invariant norm, even stably unbounded. The question is whether they are in duality. So there is an example here, Ham of R2 doesn't have quasimorphisms, however, it has. Actually, I will not show it today. No, it has unbounded conjugation invariant norm. Now, why 2 points? Well, I could have taken more than 2 points. It's the same for me. So now not 1 point. So it's just for the purpose of today's talk. The reason is that the fundamental group of this guy is F2. And on F2, I have many quasimorphisms. And if you take R2 minus X, then it's Z and doesn't have quasimorphisms. And it seems to be that this guy has a hyperbolic features and the other doesn't, and it seems to me it's just more difficult. But you're completely right. You could have taken 1 point out. It would be the same question. But I just believe more that on this guy it's easier to, I don't know if easier, more possible to construct than on the other, but I don't know. Okay. Okay, so the last definition for today. Let G and nu as before. What I mean is G is just some group and nu is a conjugation invariant norm on G as before. Then a function psi from G to the reals is called a relative quasimorphism. It should be written nu relative, but I will abuse the notation. Relative quasimorphism. If the following happens, there exists C greater than 0, let's say you can write it even greater than equal, such that for all G and H in G, we have phi of GH minus phi of G minus phi of H is less than equal than C multiplied by the minimum of nu G and nu H. Okay. And probably with this definition you're aware of, you've seen it in several, so I think certain spectral invariants satisfy this condition, and sometimes they actually satisfy this condition with respect to certain fragmentation norm. Of course, fragmentation norm you can define, your sets can be completely different, not only balls. You can talk about displaceable sets and so on, right? So this is a definition of a relative quasimorphism. So what is interesting that on this group there are several constructions of relative quasimorphisms. I probably will give you now the easiest one with respect to different norms, and there is no construction of real quasimorphism. Okay. All right, so now I will state the theorems. So before I will state the theorem, I just will need the standing assumption that in many cases it is just satisfied always. Assumption is the following, that the induced evaluation map from pi 1 of homeo 0 m mu is the base point identity to pi 1 m z is trivial. Okay. So what's the evaluation map? So you just take your group of homeomorphisms and you evaluate your homeomorphism on a point z. So this is a standard evaluation map, and this is the induced evaluation map on the fundamental groups. Okay. So my assumption is that the image of f star is trivial in pi 1 of mz. And then I will tell you when this condition is satisfied. So for example, just maybe, if m is open, it is always satisfied, because then you just can take your point. Doesn't matter where you take your point. So you take your point where it's away from the support. And then if, for example, the center of the fundamental group is trivial, it is always satisfied. If this is a group of Hamiltonian diffeomorphisms of closed symplectic manifold, this is, I think, result due to McDuff, it is always satisfied. So it's quite a general assumption. Okay. So now theorems. So this is due to myself and Yarek Kedra from last year, I guess. So let M be a complete Riemannian manifold. And let G be either the commutator subgroup of homeo 0 m mu 0 m mu or diff 0 m mu diff 0 m mu so then if pi 1 m, let's say z, admits an essential quasimorphism, which means just that it is not a homomorphism. This is only what it means. And now when I'm talking about quasimorphisms, from now on, they're always homogeneous, okay, by the definition. So I will not write this down. This is just some kind of terminology. Then the fragmentation norm on G is stably unbounded. Okay. And now let me write the same theorem in case of a symplectic manifold, so which is maybe more interesting for most of you in the case of the group of Hamiltonian diffeomorphisms. This is basically rewriting this theorem a little bit. So another theorem, again, BK. So let M be a symplectic complete Riemannian manifold so if phi 1 of M admits an essential quasimorphism, then let's say Ham M equipped with the fragmentation norm, frag is stably unbounded. That one. Okay. So now, as I said, sorry about this, I just, to simplify a little bit the presentation, I cheat a little bit during my talk, but I will tell you where I'm cheating, okay, just to be precise for this. So first, in this theorem again, if M is open, then everything is fine, and most of the work here is for the open manifolds and not for closed manifolds for several reasons. That for closed manifolds, in many cases, we know quasimorphisms already. For open, we don't know. But if it is closed and dimension is greater than equal than 4, then I have to adjust a little bit the definition of the fragmentation property. So this theorem, maybe it is true, maybe it is not. I don't know. But in order to be completely true, if my manifold is closed, then my fragmentation property has to be adjusted, is that not only that all my HIs, it supports lies in the ball, but also there exists a Hamiltonian isotopy, which is supported in this ball. So this basically boils down whether simp B, when the B is a ball and dimension greater than equal, let's say, than 4, or even than 4 we know, but then 6, is it connected or not connected? So this is a big question, and I don't know the answer, and it is used in the proof. So again, I don't know whether the theorem holds or not, but dimension 2 it holds. Probably dimension 4, I don't know. Dimension 6, the way it is stated, we need to adjust the definition of the fragmentation property, and then it is again, it holds. And in this theorem, specifically if you talk about homeo 0M and homeo 0M mu, and if you talk about the dimension 2, then I have to change this group to the kernel of the flux homomorphism, because it is known whether this group coincides in the dimension 2 with the kernel of the flux. This is an open question, and then I don't know whether this group admits a fragmentation property or not. This is the only kind of remarks about those theorems. And under what I said now, then everything is correct. So then maybe before I indicate how it should be maybe proved or approached, let me give you examples, some new examples and some odd examples. So old examples by what I mean that what we do, we reprove the known results, certain known results, but I think by using much easier methods. Okay. So examples. So take, for example, M equals to R3 minus 2 lines, 2 disjoint lines, L2. Then diff 0 of M vol diff 0 M vol is stably unbounded. So in particular, the fragmentation norm is stably unbounded, but in particular, the group is stably unbounded. So for example, I don't have to take R3. Of course, I can take S3. As I said, this is an open question for several years already, whether diff 0 of S3 volume preserving, whether it's unbounded or not. So we don't know. However, maybe you can look at certain approximation. I don't know how to say it. If you take S3 minus 2 lines, then commutator subgroup of diff 0 S3 minus 2 vol, it is stably unbounded. This is a new result. So similarly, you can take this as 1. So you can take M equals to, let's say, R4 minus 2 disjoint planes, P1 and P2, and then Ham of M is stably unbounded. Well, this is known because we know that Hofer norm is stably unbounded, but this is first time when we proved that fragmentation norm is stably unbounded on this group. It's stably unbounded. So the known result that we prove is, again, as if you take M equals to R2 minus 2 points X and Y. So the fact that the fragmentation norm is stably unbounded can be deduced from the work of Zapolsky, Večeří, and Mosner. So they do something there, and then you can deduce that fragmentation. But again, their methods are completely different. And the fact that the Hofer norm is stably unbounded, this is due to Seeberg and Polterovich. Okay, so this is those are the examples. All right, so now I have probably 16 minutes. So in those 16 minutes, I will indicate the proof of those theorems. Okay, any questions? No. Good. So the idea is the following idea. So what I'm going to do, I'm going to construct a relative quasimorphism on any one of those groups with respect to the fragmentation norm. So this is first. So we are going to construct some psi from, let's say, G. So remember from the beginning now, although I use G for a general group, this is a subgroup of homeo 0 mu, which admits a fragmentation property. That's all, okay? From G to the real, which is relative, so that it is maybe, so that is relative quasi-morphism with respect to the fragmentation norm. Frag. And the construction will be purely topological. So this is first. And second lemma, what I will not have time to prove it, but I will at least state it, that we will show that this psi actually admits a lot of properties from genient quasimorphisms. What I mean by this is that we can homogenize this. It's not always the case for relative quasimorphisms, but in this case we can. can show that its homogenization, let me put it as phi bar. First, it satisfies most properties of genuine quasimorphisms. What I mean by that, constant on conjugacy classes, and if two elements commute, then it is equal exactly to sum of these two elements. This is first, but more, and we will show. But what I'm going to show is the following: we're going to show the Lipschitz property with respect to fragmentation norm. So in this case, is phi bar of f is less than equal. There's some constant. We'll tell you later what the constant is. Then f frag. Okay. So this is the idea. So to construct such a function which satisfies these two properties, whenever you have these two properties, then maybe this is the only proof maybe I will write down, then this will imply immediately that that the fragmentation norm is stably unbounded. Maybe let me write this down. Okay, so 1 plus 2 imply the theorem, the theorems. Maybe proof. I will write it maybe later, a little bit later. Okay, it's still one line, but I need just certain notation for this. Okay, so this is the idea of the proof. So what I'm going to do now in the remaining 13 minutes is I'm going to give the construction of this guy. I'm going to state its properties. I'm not going to prove this, and then neither I'm going to actually to prove that it's relative quasimorphism. But I'm going to prove the result of the theorem and then maybe conclude with some remarks. So this is the idea for the next, if you're still not bored or overwhelmed with the talk. Okay. So now I'm going to talk about Polterovich construction, or maybe it's slight generalization, but basically it's due to him. Construction. Okay. So let G be a subgroup of homeo 0 M mu, which admits some fragmentation property, and suppose that f star from pi 1 of homeo 0 M mu identity to pi 1 M z is trivial. So let Z be the base point on M. So this is just would be the picture. So this is the picture of my manifold M. This is Z. So now what I'm going to do is the following. I'm going to take some point X here, and I'm going to take some homeomorphism here. And then given this data, I'm going to construct you a loop. Then I'm going to take the class on pi 1. And then there is some quasimorphism, because in the theorem, remember that we have some essential quasimorphism on pi 1, which I will call it phi, which is, and then I will take the value of this quasimorphism on this loop, and then I will integrate over all points. This is, I said it very fast. Now I will just write this down. So this is my data. So let me take f in G and some point x in M. So this is x. And then I'm going to take the isotopy. So what is important here is that isotopy actually lies in homeo 0 M mu. It doesn't have to lie in G. So I don't care completely whether the group G is connected or not. Okay? So this is identity, and this is F, and this is Ft. Okay, so F could be, for example, volume preserving or Hamiltonian diffeomorphism, but the isotopy lies in homeo 0 M mu. Okay? And then using this, what I'm going to construct, I'm going to construct a loop. So first I'm going to choose arbitrary short geodesics between Z and X. Just for any point X, choose short geodesic path. My manifold is complete. Maybe I don't need this assumption. I need certain assumptions on short passes, but this is just easier. So this is the short geodesic. Then I apply Ft to X. So then I have a trace. I have this path Ft to X, and this is f of X. Right? So it, of course, can intersect itself. This is just certain picture. And then I connect f of X with Z with another geodesic. So what I get, actually, I get a loop. Right? And then this loop I will denote, or the homotopy type of this loop, I will denote by gamma fx. So first, this is an exercise. This condition ensures you that this path does not depend on the isotopy. So if you take another isotopy, this is exactly what you have, the loop of isotopies, and then if in pi1 it's a trivial element, well, you can just check it. Okay? Then it's immediately that it does not depend on ft. So this is an element in pi1 mz. And then suppose I have already, from the beginning, some chosen essential quasimorphism given by the theorem from pi1 m z to the reals. So, for example, this is essential quasimorphism. So, for example, if your group is delta hyperbolic, or if you don't know what it is, just think about the group of fundamental group of a hyperbolic manifold, something like this, then you have always plenty of essential quasimorphisms on this group. Okay? So for example, this is why in the beginning I took my examples was R2 minus 2 points, which is a free group. So on free group you have really the space of quasimorphisms is infinite dimension. So now what I'm going to do, so the definition is the following: psi applied to F equals to the integral over phi bar applied to gamma fx mu, and here the integral is over m. Okay? So this is a definition of my map. Of course, what you have to show that this map is integrable. It's a little bit technical, but actually what you can show, which will imply it automatically, that the number of loops in pi1 is finite. And then automatically that this function is integrable. Okay? So this is your definition. So what Leonid did, he defined it whenever M is closed, and this is for div 0. So now you don't need this assumption. You just need to prove that this is well defined for this more general group. So this function psi satisfies the following conditions. So first, psi can be homogenized. So facts. Psi bar of f equals to the limit of, let's say, p goes to infinity of psi of f in the power of p divided by p. And this homogeneous function is invariant under conjugation, and it's on the product of commuting elements, it gives just the sum of those elements. Moreover, there is another lemma that one has to prove, is that whenever this guy is non-trivial, well, if it's essential, it's automatically non-trivial, then this function is non-trivial as well, and this is true. Okay? So then what you have, basically, you have an embedding from the space of, let's say, homogeneous quasimorphisms here to space of such functions here. I didn't say. So this is not a quasimorphism. However, the theorem that I'm not going to prove, that what is true, that this is a relative quasimorphism with respect to the fragmentation norm. And I must say that the proof is not difficult.
Can you recall what essential means?
Essential means it's just not a homomorphism. That's all. Just I need it for the theorem, but for the construction, I don't need essential. I can take anything, okay? And second thing, that this psi satisfies Actually, here I can put 3, and here I can put d phi. So I didn't tell you what it is, but so the minimal constant, what you write in the definition of homogeneous quasimorphisms over quasimorphism is called the defect of a quasimorphism. If you have an essential quasimorphism, the defect must be greater than 0 because it's not a homomorphism. The defect of a homomorphism is 0. So this is the deep psi here. So this is the precise statement here. And maybe now I have 3 more minutes. I will maybe, using these 2 propositions, I will finish the proof of the theorem right here. OK? So, right. So let, again, psi bar from pi 1 m z to the reals as above. And there exists f in G such that psi bar of f is not 0. So this is due to lemma that I told you that if this guy is not trivial, then this guy is not trivial. Not trivial, it means exactly that there exists a diffeomorphism on which it is non-trivial, non-zero. So I'm just taking such diffeomorphism. Then, maybe I'll write this down here. Limit, when p goes to infinity, of f in the power p frag divided by p is greater than equal than limit of psi bar of f in the power p divided by 3p multiplied by d phi. So this is exactly what I use here. Okay? But this proposition uses this proposition. Okay? But you remember that this guy is homogeneous, then p I can take outside, right? Which equals to psi bar absolute value over f divided by 3 d phi. And this is the constant, for example, that you get, so your norm is stably unbounded. And I think this is exactly the right time to stop my talk. Thank you.